All right, and welcome back to the course. So we're looking at essential singularities and really the behavior of functions near essential singularities and how wild this behavior is. We're going to prove the Casorati-Weierstrass theorem. This is subsection 5.2.3. So first, jumping into the term, let's look at sort of a typical example of an essential singularity. So let's look at e to the 1 over z. Now, that's sort of our basic example of an essential singularity. Now, it's really hard to draw a graph, right? Because I'd need 2 real dimensions for the domain and 2 real dimensions for the codomain. I'd need 4 dimensions to draw a graph. But this is actually a neat way of visualizing. So we can visualize the modulus by brightness, right? So completely dark or black is 0, right? And then it goes to just, completely bright, which is just going to be white. It's just brightness at full blast. That's going to be essentially just white, right? So that's infinity, right? So that's giving you the modulus, right? And then so that's the size, right? And then the hue, which is really sort of the where on the color wheel you are. So like what are you using green, red, blue, stuff like that, right? That's going to be the argument, right? So that's kind of goes around in a circle, whereas brightness sort of goes in a range, right? So you can think of that range as 0 to infinity, and I can think of hue as sort of going around in circles. So that's naturally the argument, right? So over here, what you see is that when I approach sort of from the negative side here, it's sort of everything becomes very dark, right? Because it's actually e to the 1 over z is actually going to 0 there, right? And so it's e to the z is small in this region over here, while in this region it's sort of big, right? Now that's not that's just talking about the modulus, right? But if you notice that the colors, right? I have okay, so I'm sort of going through different colors, and then I'm repeating, and then I'm repeating and repeating and repeating as I'm going towards. I'm actually cycling through all the arguments over and over and over and over, right? And then kind of being close to 0 on one side and close to infinity on the other side, and sort of everywhere in between. So what we actually get over here is that in every neighborhood of the origin, no matter how small of a neighborhood I choose, I will always get all moduli and all colors. Well, I will never get 0. Modulo 0, it's e to the 1 over z is e to the z is never 0, right? So I never get 0, but I get everything else actually. No matter how small of a neighborhood of the origin I take, if I plug it into e to the z, as the image of that is going to be essentially everything except 0, right? So it seems like, well, it actually is. That's not too hard to to see for this specific example, right? But we get near 0, we achieve every value except 0, right? So not quite every value, but almost every value, right? All right, so this is the Casorati-Weierstrass theorem, the promised Casorati-Weierstrass. Right, so suppose that I have an essential singularity. So suppose that I have a holomorphic function f, and it's holomorphic in this punctured neighborhood, so u minus p, and it is an essential singularity at p, right? So then what we get is that for every punctured disk that's still in u, right? So I want a disk around p, an arbitrary neighborhood of P, and then I'm taking the P out, it's still in U, then the image via F of this punctured neighborhood, well, so not necessarily everything, but what we're going to prove is it's dense, right? It's the complement has empty interior, right? So it's dense in C. You're definitely getting almost everything, right? Now the intuitive idea of the proof is, well, if the image had if it was missing some open set, so if the complement had some interior, well, then there would be at least some disk, right? So if a whole disk is missing from the image, well, what we could do is, and LFT is some automorphism of the Riemann sphere, right? So we can take that Q, the center of the disk, and let's just map it to infinity by an LFT, and then we're just gonna get, that this missing disk is gonna be this neighborhood of infinity, and so the complement of that is just gonna be a disk, right? And so we're actually gonna get that after composing with this LFT, we get a function which actually maps into a disk, so a function which is bounded, and so the Riemann extension applies, right? We can extend through the singularity, and that's going to basically mean that it's either going to be a pole or it's going to be a removable singularity, but it cannot be essential. All right, now there's a much stronger version of this theorem, but we're proving this because it's easy, right? It's exactly the opposite of what Kennedy said, right? We don't do this just because it's hard. We do it because it's easy, right? Because we can. So that's why we're proving Casorati-Weierstrass, because it's easy. Because basically we have all the machinery now, and we can, it's almost immediate, as you'll see. Well, as I've outlined here, and you'll see that details are actually very simple too. But the more general version of this is the Picard's theorem, and what it says, it basically still talks about this guy, but it says that you actually get either all of C or all of C minus some point, some single point. So you can miss. So basically, it's like e to the 1 over z, right? There we're missing 0, but that's the worst that you can do. So you can either hit everything or hit everything except 1 point. All right. So let's prove it. So let's just go through this proof. So suppose, okay, we have this holomorphic function with an isolated singularity. We're looking at this disk, right? So that's the disk from the punctured neighborhood. Sorry. And we have this disk around some point Q, which is actually contained in the complement of the image, right? So if the image was not dense, there would be such a disk, right? Now let's define this function g on this punctured neighborhood, right? By taking 1 over f of z minus q. Now, f of z is never q, right? Because the disk around q is actually in the complement of the image. It's even more. It's actually in modulus is not just not 0. This is always bigger than s, right? So for all these guys, we have that you're outside of this disk, right? So the f of z minus q has to be in modulus at least s, right? That's basically just the definition of what this means. If I take 1 over that, that's g. Well, that just says that g is less than or equal to 1 over s, right? For all z in this punctured neighborhood, right? So that means it has a removable singularity by the Riemann extension theorem, right? And so we can just assume that g is actually defined at on the entire disk, not just the not just the puncture disk, but you know, on basically it's defined at P, right? We just extend it, and let's just assume that G is the extension, right? Then what do we have? We have that F is equal to, well, it's 1 over G plus Q, right? And just solving for F over here, right? Now, so for all for all Z where in this puncture disk, that's definitely what it is, right? That's where F is defined, right? And we just define G so that this is true, right? Now, but G is defined at P, right? G is holomorphic at P. So if G is 0 at P, well, then I am, and maybe this is not quite defined at P, but it means that that 1 over G has a pole, so 1 over G plus Q also has a pole. Q is just some constant. So that is a pole, right? So if G of P is 0, then F has a pole at P. If G of P is not 0, well, then if I divide by it, I still get something holomorphic, right? So this is actually then holomorphic in the entire disk, right? So then F has a removable singularity, right? Well, those are the only possibilities. I mean, G of P can be either 0 or not 0, right? If it's defined there, right? So that's that's the end, right? It's essential singularity didn't come into the picture, right? So the point is this this application of the Riemann extension theorem, right? That if we miss a whole disk, then we can actually make a bounded function, right? That disk can actually be a neighborhood of infinity after an LFT, right? So that's why if as an essential singularity has to sort of get close to everything. All right, now a couple of exercises. So the first one is prove the converse of Casorati-Weierstrass. That's kind of a trivial thing, but actually it's a it's an if and only if. The one that we stated is the more useful one, more useful idea, but it goes the other way as well, right? If you have a function such that the image of every punctured neighborhood of an isolated singularity is dense in C, then it has to be an essential singularity. Okay. And there's another one. This is related to an exercise that we talked about last time. So this is basically just building up on that, making it more of a more general statement. So if you have an isolated singularity and you take so G has an isolated singularity and you take e to the G, then basically there can never be a pole, right? It's either an essential singularity or it's a removable singularity. Those are the only possibilities, and it's essentially because if G had a pole, then you would actually have an essential singularity, and if G had an essential singularity, then you have to prove that will still give you an essential singularity. All right, now suppose that we have an entire non-constant function f. So now we're not talking anything about what kind of singularity it has at infinity, but it just has some isolated singularity at infinity. Now prove that the image of f is actually dense in C, right? So you really have to do this in, you have to think of two possibilities. Either it has, it has a pole, or it has an essential singularity, right? Or you could prove that if it has a removable singularity at infinity, it's actually constant, right? But you basically sort of argue by cases, right? And so prove that f of C is dense, right? Now this is well, actually, another version of Picard's theorem. So it's usually called the little Picard's theorem, because it's sort of more special. It's just about an entire functions and their singularity at infinity. And little Picard's theorem basically says the same thing. It's f of c is not just dense; it's actually everything minus a point or everything, right? It could be everything, right? Like the function, z, right? It's just the identity, right? Well, the image is everything, so it could be everything. E to the z. Okay, you're missing 0, right? Otherwise, it's those are the only possibilities, right? You can miss 1 point, but you prove this simpler version. Just suppose just prove that it's dense. All right, so that's it for today, or for this lecture at least. So it's next time we're going to look at meromorphic functions quickly. So those are functions that are quotients of holomorphic functions. So functions with isolated singularities, they could have poles basically. So all right, so that's next time. So see you then.